Hi, everyone. This is a bonus lecture on input-output LCA, and I'll follow this with a little bit on how to use the open LCA model for input-output LCAs. So totally different stuff than what we were learning in our LCA bootcamp. That was a process-based approach, and this is more of an economic-based approach. So we'll go through a little bit of the details on the model, and then I'll show you how to use it. So input-output LCA kind of addresses one of these issues that pops up in process-based LCA, which is the boundary. Where do we set our boundaries for life cycle assessment? When we are doing process-based LCA, there are a lot of things that can be hard to account for because they might be a little bit beyond the physical boundaries, might be hard to collect the data. And we want to include all the important processes if we have time and financial constraints. So that conventional LCA approach for a lot of the process-based LCA could be thought of as a bottom-up approach, right? Where you're here at the bottom, grabbing all the individual supplies and products and things, and weighing them and figuring out how they work. But there is kind of what we would think of as a top-down approach using these input-output models that are a lot more comprehensive in terms of what they include in the model, and they give a great top-down view. So basically in EEIO models, the boundary is the entire economy of a country or region, and it recognizes all those interrelationships in the industrial sectors. The EEIO models products are representing an average product, not a specific product. And so that's one of those limitations where if you want to, this is where it's good for high level kinds of assessments, but not for product level assessments because of the boundary conditions within an EEIO model. So we have used EEIO models quite a bit in healthcare. The big ones would be coming from Jody Sherman and Matt Eckelman. Looking at the national level emissions, this was all using EEIO data. So these are changes in healthcare spending and how that correlates with changes in emissions. And there's a lot of work that went into these studies, but EEIO models tend to be in some ways a little bit easier to use because you already have the cost data readily accessible in most cases, right? So all of this work that you've been putting into your projects to collect the actual detailed information on a process level, I'll say, can be often easier to do it with an EEIO model because the price information is usually more accessible. Not always true, but typically true. And so you can imagine, to go back to this example of the US healthcare system, if you wanted to analyze the footprint of the entire US healthcare sector, doing it in a process-based way is insane. It's probable that you could do it, but not really possible. No one's going to spend their whole life doing this, and that's exactly what it would take. So the EEIO models make it easier to have these high-level summaries. So where do these EEIO models come from? It's a combination of economic data and environmental data. So the economic data, there's a little history to this. The EEIO models are an economic thing, truly like just input-output is an economic approach. It was developed by Wassily Leontief, who was a Nobel Prize winner in 1973. And basically what it does is quantify the interrelationships amongst sectors of an economic system. Governments started using EEIO models, creating EEIO models to track those economic dependencies. And then you can basically take those economic dependency data sets and extend them into other analyses like how much energy is being used or what's the environmental impact of all those different things. And so that's basically how this model works. What Leontief was doing was essentially trying to, it's a lot of linear analysis, so mathematical approaches, where you basically have a vector of sector outputs, basically money, that's needed across the upstream supply chain to produce the final demand throughout the entire economy. So it's a little bit complicated. I'm skipping over a lot of the details, which if I were doing a class on this, I would actually have you do some exercises so you can dig into it a bit and feel how this might work and how you might keep track of spending. But basically, our economy is interdependent, right? The steel industry makes steel for other industries, but it also needs to make steel for itself, and other industries need to provide it with water or electricity or whatever else, but those industries also need the steel. So there's a lot of interdependencies in our economic system, and it can be really hard if you think about it from a process-based LCA to kind of separate those out, tease them apart, and figure out, what kind of unit processes you might want to include. And the EEIO model helps deal with that kind of circularity and all that kind of product demand in a different way. So there's a soda exercise reference on this slide, and that would be one of the things I'd have you work through. But for building an EEIO model, usually the way that this is done is the government collects some statistics, might survey different industries. They often organize the economy into specific sectors, and as you would imagine, there are set ways of doing this. And we'll talk about those later. And then the government would survey those industries. So which sectors do you purchase goods and services from, and how much do you purchase in price value? And then which sectors do you sell to? And they collect this information for as much of the economy as they can get their hands on, I suppose. The surveys might include census of manufacturers, census of transportation, an economic census, which is done every 5 years or so. I think we're due for one in 2020, which obviously didn't happen. And so the EEIO models are a little bit dated at present, but hopefully there'll be a new one coming out soon. And that's just the economic model that the government sets up. So these classifying industries into sections is something that governments have been working on for a while. And EEIO models are sector-based, meaning they often build off of what the government already has for classifications, but they may have their own classifications on top of that. Usually they're very related, but the EEIO, meaning the life cycle assessment EEIO models, might be a little bit more aggregated than what we see in these economic models. So here are some of the typical classification systems that a lot of countries use for tracking their economic data between sectors. There's NACE, which is for Europe, ISIC. I actually don't know who uses ISIC, but SIC is another pretty popular one. The one that we encounter most often, of course, in North America is NAICS, the North American Industrial Classification System. And so the NAICS codes are a label applied to each economic sector, and that's the key to using EEIO LCA models, is knowing which sector your spend is coming from. And so you'll probably, if you use this model quite a bit, you'll become more familiar with NAICS codes. But there are other EEIO models, other EEIO LCA models that might use these other classification systems. So if you're in Europe, it might build off of NAICS codes, in which case you'd want to learn a little bit more about how those are divided up. I think the classifications are fairly similar, but it's a lot easier in the manufacturing space. When you get into the services sector, that's where things get a little bit funky. There are lots of different schemes for doing this. And so you might, just do some Googling. So here's kind of a high level overview of how these things are divided up, where you have SIC on the left and NAICS on the right. NAICS gives you those numbers as the high level overview, right? So any type of manufacturing is going to start with the NAICS code of 3132 or 33, and then there's a bunch of other numbers behind it depending on how far down the manufacturing sector you go. And so there's a interactive site that the US government, the Bureau of Economic Analysis, has that you can learn a little bit more about those input-output data. And there's annual tables, but the benchmark tables are about every 5 years. And the latest release was in 2013. So again, we're overdue for it. I think the pandemic kind of messed some stuff up. And these are, of course, US-based models. Everyone's going to be a little bit different. And there are other data available elsewhere as well. The NAICS code is usually 6 digits, though I think they can get longer if you're even more specific, but 6 digits is pretty standard. The first 5 digits are fixed, and the 6th is for country specifics. So here's an example where you have manufacturing, right? So this is like an industry sector. You have computer and electronic manufacturing, which is 334. And then within that subsector, you have an industry group of manufacturer reproduction, and pre-recorded computer CDs, which Probably nobody knows what they are anymore, but anyway. So those are an example of like the NAICS code and how it comes together. For the IO model, this is a really simplified view of what those input-output economic models might look like from the government, where you basically have certain sectors, 1 through 3, and that could be your manufacturing or healthcare or whatever. And you have inputs to those sectors and then outputs to other sectors, where X11 here would be kind of circular. And so you have final outputs, final demand, right? And it's one of those great tables. So there's kind of, you could think of it as a recipe for making an output from sector 1 here is output from sector 1. I feel like this might be circled the wrong direction. Output from sector 1. Sorry. So the outputs from these various sectors are really the summation of the inputs from these other sectors, right? So it's kind of showing you on an annual basis how things flow through the US economy or any government's economy. Here's some of the mathematics for it. Again, I'm going to skip over some of this just because it dives in a little bit deeper than you probably want to know, but do know that in our recommended LCA textbook, the free online textbook, lcatextbook.com, they have a section on IO models if you want to read up about how this works. The mathematics is actually not horrible. If you've done any kind of like engineering or mathematical work, this is actually fairly simple math. But for those of you less comfortable with math, it probably be less comfortable. It's matrix math, basically. And so if you think back to our generic unit process, it's kind of a similar concept. It's just at a much higher level. So we might have a car that we're pulling up in, say, EcoInvent for a unit process. But what the IO unit process does, if you will, is it's using inputs from all across the sectors, right? So you've got all this different monetary inflow, and the outflow is maybe like a $20,000 car. I think these slides were made a while ago. And the thing that we're missing from these IO models at present, what I haven't talked about, is how the emissions and the waste are accounted for, but that's something that's kind of overlaid on top of the economic data. So if we're using an IO model, I'm going to skip over this because this isn't using the environmental, like the EEIO LCA model. This is actually talking about using an IO model itself. And it's mostly about linear algebra and those kinds of approaches. So I'm going to skip over this for now. For the environmental impacts, let's see if I can remember this equation here. Oh, that's all I have for this? Well, that's sad. There's definitely a matrix in there, inverted, but I don't remember what R is. Do we have what R is? Flow factors in units per dollar. So this is a part, well, for me, it gets a little bit cloudy, but basically they've created another vector, we'll say, could be a matrix that's overlaid on top of the IO data that shows for each sector, like how many emissions you'd expect to see per dollar spend. And these can be direct emissions from like the factory assembly or the first tier suppliers who are delivering to that assembly line in the case of the example of automobile production. And they can be indirect emissions like the emissions from suppliers of suppliers' factories or electricity purchased by those supplier factories, right? So this is where, because of the nature of the IO models, you have a very inclusive boundary condition where you can get to more of those indirect emissions just because they're inherently built into the model. And so anyway, where do we get that R matrix from? The R being the environmental impact. We can collect data on the electricity consumption of certain sectors. And this might come from a survey that the Department of Energy does. And that kind of NAICS mapping to IO mapping is fairly easy. You might get other manufacturing data in SIC, which can be a little bit harder. And you repeat this a bunch of times for all the sectors. You're basically trying to pull in any information on how many emissions might be coming from these groups by looking at electricity consumption and other things. And you do this for all the different sectors, and eventually you come up with a matrix that you can then map over the top of the data spend. So that's the magical part. I don't know exactly how those models are created. But if you go to an LCA conference, you'll probably meet some of the people who've made them and they can explain it a little bit better. Sorry, I'm rushing through this. And there are, of course, textbooks that will help describe it as well. So most input-output data sources, LCA data sources, are free and publicly accessible. You will see some IO models included in CIMA-Pro, but I believe those models are a lot older, so people don't typically use the ones that are in CIMA-Pro. That may not be true for the European ones, but it's certainly true for the US-based ones. There is a really popular one that you'll see referenced in a lot of papers, mine included, and it was a Carnegie Mellon University model from 2002. I don't know if the website is still functional. It got a little bit weird to access in the last few years. Right now it's 2023. And partially, I think that's because the faculty members who ran this model left CMU, and so it may not be available online anymore, but it was a nice user interface online, and you didn't need really anything extra to use it. And they were using IO tables from the BEA, EPA data on toxics and air pollutions and greenhouse gas, non-carbon dioxide greenhouse gases. They were using DOE data for energy and carbon dioxide, and the DOT, Department of Transportation, for transportation energy data. And so they overlaid all of that different environmental data on top of the IO tables for the US. And it was a really great source of information for a long time. But of course, 2002 is now over 20 years ago. So it is a bit older. And as you can imagine, in the last 20 years, lots of things have changed, including our energy sources, and certainly what kinds of industrial processes are out there. Particularly, you think about technologies and how much that has shifted in the last 20 years. So there are lots of changes to these that make these older models a little harder to trust. It's not to say they're not still good, but they do have their limitations. There's a new model I'm going to show you, but for now we'll just come back here. 29 food section. I'm going to skip this example. I think you kind of get it, but the big thing here for IO models is that there's a lot of work that's put into making these IO models, IO LCA models, because you have to do a lot of conversion. It's a lot of work. That's all I can tell you. So the people who put these models together spend a lot of effort collecting the environmental data, mapping it to the IO models. And they have to do some work with aggregation within the IO models, depending on the data sources for the emissions. So definitely a lot of work. But the great payoff is that it can be more up to date. If it is a newer model, it usually represents the emissions a little bit better than even some of the unit process data, where it may not be updated quite as well. EcoInvent's hard to tell exactly when a certain unit process was last updated. And so in this case, the whole model is for a specific year, and you can feel fairly confident in those numbers, at least up until that year. The NAICS codes can really help, because it's a coded system, it can really help with international comparisons, though there are some limitations to that. So here's one of the models. This is the Carnegie Mellon model that I mentioned, which I don't know if you can still access it online, but it used to be a website. You just come in and you actually use the tool right on the website. The new IO model is what they call the US EEIO. So it's the United States Environmentally Extended Input-Output Lifecycle Assessment Model. And this one, you can download a file from data.gov. And I will kind of walk you through how to do that. You will likely need to install OpenLCA, which is a different to CIMA-Pro, but it is a lifecycle assessment user interface. And with OpenLCA, you would open, within OpenLCA, you open the file you downloaded from data.gov, and then you can start using the model within OpenLCA. The alternative here is that you can kind of manage the model on your own if you're comfortable with coding and with linear algebra. You don't necessarily have to open it in OpenLCA. It's just, for most of you, you're probably not super confident coders, and so having a user interface is going to be a little bit better for you. Anyway, the other thing to make sure of here that I have a note on the bottom is that if you're using OpenLCA, I know it's a totally different user interface from CIMA-Pro. You need to install as well these impact assessment methods. So you would go to the Open LCA website, download this as well. Otherwise, you won't be able to analyze the data. It'll just give you the emissions and not the impact. So that's a side note. Here's kind of a view of these IO models. I should check to make sure that this table is still available or still the most recent. But what you can see, as far as I'm aware, this is the most recent data. There's an Open LCA link here. And the rest of these you can see are matrices that you could potentially download. The US dollar year is 2013, so that's the most recent monetary value, even though the input-output data is from 2007. So you can see the age here, and it's, again, you have a version number on your data sets, which is important when you're reporting out. It could be that this US version 2.0 has finally been made available for OpenLCA, but I'm not sure. You can see the US dollar year hasn't really changed either, so there's more sectors though. Anyway, interesting information on it. For using these models, it's pretty simple. The first thing you got to do with any LCA is collect your data. So you want to figure out how much spend you're looking at and from which economic sector the spend is coming from. So in the case of like a hospital, your major spending categories are probably going to be like medical supplies and pharmaceuticals. And you're going to want to go through some NAICS codes. What you're probably going to want to do is actually open up the EEIO LCA model to see what kind of sectors are there, because there's a lot more aggregation in the LCA models than there are in the IO models. But you're going to have to map whatever monetary data you have to a sector. And so that's the first step. The second step you'll have to likely do, unless you have data from 2013, you're going to need to deflate your spending data. And so basically, if you purchase something, this is this year, 2021, obviously slides are a little bit old, but if I'm using spending data from 2023, let's say, or 2024, and my latest IO model is from 2013, I need to change that monetary value to the value it was in 2013. And there are tables we can use to do that. It's simple. It's very simple math on this, but you basically just need to make sure it's in the right year dollar value. So for doing this, at least, again, we're going to concentrate on the US models. There are other countries' models out there and other currencies. So this is US dollar specific. You can come to the US Bureau of Labor Statistics and look for a producer price index, a PPI. And this is basically measuring the average change over time in selling prices for domestic producers based on their output. You can ignore that asterisk note there because that's only for the Carnegie Mellon model. But basically, once you go to the BLS website, you would look for the producer price index, this PPI table. Industry data here is pretty good. And I usually would select either one screen or multi-screen. Either of these is good. The top picks only gives you certain sectors, so it's a little bit clunky. But anyway, one screen or multi-screen are good. And you search for your economic sector, right? So if it's medical device manufacturing, you'd search for that sector, and you would open it up. So you can find, well, in this case, we've got canned beer and ale case goods as the example. But you would basically find that sector and see what year the data are. So you can see the table that was pulled out here for this particular example went to 2011, right? So I can select the year up here. And if 2021 was the year of my dollar spend, then I would have to convert, let's say I had $100 that I spent in 2021, but the year of my LCA model is in 2013, I'd have to use this ratio of the 215 to 221 to deflate my $100 into something like, I don't know, was it $95 maybe? And $95 is what I would put into the model. So hopefully that makes sense. But we basically need to convert our dollars into the year of the model from whatever year we're using or whatever year our spending data is from. You can also download this table in Excel, which I recommend doing just so you don't have to keep coming back into the BLS website and finding this if you need to do the calculation again. And usually over time, items inflate, though there are a few sectors where prices have been going down, like CD sales. So it may change. But basically this table keeps track of things where the base year is like 100, and this is where it's gotten to by whatever time frame you're looking at. So you can select the year, hit go, and it'll update the table. And you can export it as an Excel file and start playing around with your data. Once you've deflated it, you just input that value then into your LCA model. So you would do it, in open LCA, you would select the sector, put in your monetary spend, and it would spit out, hopefully, your values. And so that's kind of how you use this model. The pros to EEIO LCA, it's relatively cheap and easy. So you just need price data in a sector, which most companies would have data on how much they're spending. So it's pretty easy to get a hold of. It's great for high level or top down kind of summaries. So right, that country level or industry level emissions. And you can scope emissions for a company with relative ease compared to a process LCA. And you overcome some of the data limitations of process LCA through a hybrid approach, meaning I have used EEIO models quite a bit to model pharmaceuticals because we don't have any process-based data for pharmaceuticals. It gets a little weird when you're combining the two approaches because the boundary conditions are a bit bigger in an EEIO model, but it can still be useful. And circularity is built into this model, so you have less allocation issues you have to worry about, which can be kind of nice. The cons to an EEIO model is that they have really big boundary conditions and you often don't really know what's included, right? So you have a little less control and less clarity. You cannot compare products within the same sector. So you can't do detailed LCA here. And so the example that I like to pull on, which I think I used in class, is, is the manufacturing of a name brand drug different in carbon emissions from a generic drug? I don't know. And we haven't really seen data that shows us one way or the other. An EEIO model would tell you that the name brand drug has a much higher carbon footprint than a generic drug. And from one perspective, I could say, yes, that's true. From another, I could say, no, it's not. The no, it's not is, well, if it's the same drug in the same format, it should be manufactured the exact same way. So the emissions should not be different realistically. But what the EEIO model does is it's also including marketing, transportation, R&D of other drugs that never made it, like a whole bunch of things. So it's a much more expansive boundary condition, which some might say is more accurate. Others might say, no, I just want to know this product and not all that extra stuff that's going on in the industry. So that's where it's a challenge, pros and cons. You can still have quality issues, certainly with the temporal stuff, right? So these are older models oftentimes, and you still have a lot of that issue. And there can be a lot of regional variation that's maybe not accounted for because you're looking at a national sector. So those are things to keep in mind. I'm going to break here and I'll see if my OpenLCA is functioning. I haven't used it in a while. And I'll create a new video for the OpenLCA.